Right. Hello and welcome to our session on, well, our first session on related rates. Just zoom in a little bit here. Get started. Now, when it comes to the topic of related rates, we have a little build up to do first before we can get to the more practical questions. So it sort of comes in two parts. That before I can handle the practical questions, I need to just look at functions and derivatives um, a little bit more first. So let's say so far we've looked at derivatives in a certain way, or finding the derivative rather. Given a function, let's say for example f of x. Let's just make it simple. There's no need to be complicated here. It's just a concept that I'm introducing. Let's make it nice and straightforward, right? We find the derivative, find the derivative. By now, hopefully that should be quite easy. Bunch of basic properties, and I get 3x squared plus 4. No problem at all. Well, I hope so. Now, this was straightforward because the function was quite straightforward. Even if I make this right-hand side more complicated, the fact that I have a function y equals to stuff in x makes my properties convenient. But I could look at this in a different way, and that way is going to become crucial when things get a little bit more complicated. So I guess it's not a different view, it's just a more general view of this exact same thing. That instead of looking at this as a function, if you go way back to the very first introduction lecture where we talked about functions and equations, I said that I could look at a function as an equation. And some equations where I can solve for y, I can then see as a function. Depends on the view. It depends on the goals that I have, what I want to do, that I can flip back and forth between these often to suit my needs. So instead of looking at this as a function, I could look at it as an equation. I could shuffle this, right? This could come from, let's say, could come from something that's a little bit more complicated, I guess. I could say 4x minus y equals negative x cubed. That's the same equation, right? It's just shuffled around a little bit to make it look scary. It's the same thing. And by solving for y, it just looks a little nicer, and I can then identify it as a function. But it doesn't have to be. It's just an equation. And the graph of this equation consists of all the points, x and y, that satisfy this equation. So instead of seeing it as an input-output function situation, I just see it as a bunch of x, y value pairs satisfying an equation. But remember, this is the same. This is the same thing. So that means I should be able to find the derivative as well, the same derivative. But I'm going to do it in a different way. Now, this being an equation, I'm just going to see it as a left-hand side equal to a right-hand side. People get confused. What is this LHS? I just said left-hand side, right-hand side. It could be up here as well, right? And we'll look at that in a second. But let's take the simplest version. Now to find the derivative, I'm going to do something seemingly different, but it's not different. Just a little fancier. To find the derivative, I'm going to see this as an equation. I have to forget this left side for a second. And it actually becomes easier the more complicated the equation gets. Whatever is on the left is equal to whatever is on the right. Equal means they are exactly the same. So their graphs are the same, their behavior is the same, their rates of change are the same, everything's the same. So their derivatives will also be the same. So if I take the derivative of the left-hand side of the equation, it has to be the same as the derivative of the right-hand side of the equation. The same. So their properties are the same. Now the derivative of the uh, left-hand side, I can simplify to just y, and this certainly simplifies to any notation you want, right? dy dx, or y prime, or whatever notation. These are all the same thing. On the right, however, I have something more than just a single variable. I have something more interesting that I would need my properties for. But still, not complicated. Same properties will give me the result. Now these are the same, right? As they should be. Just a different view of the same thing. Different view of the same thing. Now, if I take this version, for example, remember, it's the same equation. Same equation. And I see, let's just see here. I'm going to peek ahead. 4x minus y equal to negative x cubed. I just see it as a left-hand side and a right-hand side of an equation. So because they are the same, regardless of how complicated they look, regardless of if I understand how to see this side on its own, doesn't matter. This equal sign says it is the same. Therefore, the derivative of the left-hand side is the same as the derivative of the right-hand side. If things are the same, they change in the same way, derivative is just the rate of change. So I'll now fill in what the detail is. Oopsie, not a round bracket, square bracket. My big D notation as a square bracket. I'll put in what the detail is. And now I just go about my business, forget everything else. When I look at this, I'm just looking at a derivative question. I don't care where it comes from. I just look at it, what it is. I'm going to use the difference property to separate the terms, just to emphasize that those properties are still there. I'm going to look at the right-hand side later. This derivative, yeah, constant times a function property, power rule, it's 4. This derivative just has a y in it. It's the derivative of y. Because in this version, in this equation view, I don't necessarily know what y is. It is, in this case, a function, but it's hidden. It's hidden away. Before we finish, I want to clarify that here, in both of these versions, let's say over here, space here, I'm going to go up here. When I solve for y, I can then see it as a function, and I say y is explicit or explicitly defined in terms of x. Y is explicitly defined in terms of x, a function. But when I look at the equation version, that's maybe a little bit more shuffled. It's the same equation. This one doesn't exactly show what the function is. And maybe I'm not interested to solve for y. And maybe I can't solve for y because it's too complicated. but it still defines the same thing. We say y is implicitly defined in terms of x, I guess. No, we don't really say in terms of x. It's implicitly defined by the equation. It's not in terms of x because I can't see it all in its as a combination of x uh, variables. But it's still defining the same thing. One is clear, explicit. One is hidden, implicit. Okay. So when I look at the hidden version, even though it's a simple equation in this first case, or a more complicated equation, more shuffled around equation, we call the derivative of the left-hand side equal to the derivative of the right-hand side. We call that implicit differentiation. When the function is a little bit hidden, but I have it somewhere in this equation. It is defined. I don't know it. I don't know the function y. I just take the equal sign and do implicit differentiation, which says the derivative of the left-hand side is equal to the derivative of the right-hand side, which has to be true because equal means the same. I then go about my business, filling in the left-hand side. We're back here, filling in the right-hand side, and then just go to my derivative properties that I already know. There's no new derivative properties at this stage. Now here, when I look at the derivative of 4x, basic properties 4. Here I'm looking at the derivative of y, and at this stage, because I didn't solve for y, I technically don't know exactly what this y function is. I know it's a function, and this big D notation is just asking for the derivative. I don't exactly know what that is, which makes sense because I'm trying to find it. I won't know what it is. That's the thing I'm trying to find. So I just rewrite this into a different version because I like the look of the little d notation. You can write y prime. You can keep it as the big D notation. I don't really care. They're all interchangeable. And then on the right-hand side, that asks that I do some basic constant times a function and power rule properties to get negative 2, not negative 2, negative 3x squared. So the fact that the original equation was a little bit more shuffled around doesn't change what I do. I am looking for the derivative of y with respect to x, solve for dy dx, and I'll again get negative 3x, no, not negative at all. This guy moves to the other side, this guy moves to the left, so 3x squared plus 4. Same thing, right? It's the same thing. It has to be the same thing. It came from the same equation. How can it not be the same thing? It has to be. It has to be the same thing. So it's all just a matter of where do I start? Do I start with a nice clean function? Great. Do I start with an equation, but it's kind of in function form because y is already solved for me? Also great. I kind of have a choice. And I would use this left version because I see the function right there. Easy. Or do I start with something that's a little more hidden? I could solve for y, but we'll soon see that we can't always solve for y. But we can always do implicit differentiation. Okay, so this is part of something bigger than functions that we're trying to get to. Implicit differentiation. Implicit differentiation. Let me just see my space here. I have some space, but I don't need to use. Just make a new page. So, like I said, there are more things than just functions. Let's write that down. We are not really spending too much time with these things, but there are more general I'll say things than just functions. And casually speaking, there are things that come from equations where I can't solve for y. If I can solve for y, that's a function. If I can't solve for y, it's part of this more general structure called relations. Now, those things are not easy to work with and much more varied within that concept. But very loosely speaking, if I can't solve for y, I still have an equation, right? There are still x and y points that give me a graph and all good things, possibly. Can't solve for y. I don't have a function. It's a part of a more general thing. We've seen these things before. We've seen equations like this, or you should have. Maybe you blocked it out. That's an equation of a circle. Or let's say it like, yeah, so let's say it like this. Equation of a circle. Meaning there's a bunch of points. Let's draw the circle. Why not? Circle. It's not even a difficult shape or a difficult graph, right? Something very familiar. Now, in hindsight, I should have started with my circle. This is gonna suck. I'm gonna have to backtrack. I forget the shortcut that makes the circle from the center. I could just sort of drag it from its side, which means I need to put the circle down and then make sure my axes are centered, right? Just the drawing little issue based on the tools that I have. There's a shortcut that expands the circle from the center. I don't remember what it is. Doesn't matter. Circle, radius 1, centered at the origin. We've seen this before. High school stuff. Easy. But what they didn't tell you is that this is part of this more general relation family because it's not a function. I can't solve for y. Let's say I can't uniquely solve for y. Now you can in high school uh, they might have written you can write y equal to plus or minus square root of 1 minus x squared. Right. But there are two things here. For example, if I pick a half, let's say I pick 0.5, y value that corresponds to 0.5 is not unique. There's a plus and there's a minus. And that is not a function. A function has a unique output for any input, a unique y value for any input x value. If you look at a graph, you might remember the vertical line test. If you draw a vertical line at any spot on the graph, it can cross the graph at only 1 point. This crosses in 2 points because there are two y values corresponding to one x value. Now, conceptually, that's a little weird. How can I put in one x value but get back two y values? Yeah, it messes with my head a little bit if I think about that too much. The input-output idea that I use for functions kind of falls apart. It's more complicated than that. But I have a graph. It's nice. It's a simple circle. So it doesn't have to be weird to be a step away from functions. I still have an equation. There are a bunch of points, a bunch of x, y pairs of values that satisfy. There's infinitely many of them that satisfy this equation. It's just not a function. But I have a graph. The graph is nice. The graph is smooth. The graph is not strange at all. Which means at this point up here, maybe, I can and should be allowed to ask about slopes of tangent lines. And that is still the derivative. That is the derivative question. So I don't have that strange a situation. I should still have a tangent line there, which means that tangent line has a slope, and I need to be able to find the slope. How do I do that? It's not a function. I use implicit differentiation. This is where implicit differentiation is necessary. It's crucial. So let's say here, to find what was that? That was supposed to be an S. Slope, excuse me, or derivative, implicit differentiation. Derivative of the left-hand side equals derivative of the right-hand side. The slope is dy dx at that x value, right? Still the derivative. I'm trying to find it. Implicit differentiation helps me to find it, allows me to find it when I can't solve for x. Now, yes, there are some of you that say, well, sure, I could just drop the negative, then I do have a function for the top half of the circle, then I can go back to my chain rule and stuff like that. Sure. That's only because I chose a very simple relation, a very simple equation that you can sort of cheat your way through it, that I can cut in two. I can very easily, and we will, give you one where I don't even know what the graph looks like. It's much more complicated, right? So I can't shortcut and think that's going to work every time. Just pick the simple circle to show that you've seen this before. Now, I have my sum property. Sorry, my square brackets don't look like square brackets. It's very unacceptable. And, well, we won't finish anything. Let's just do it all at the same level. Okay, so some of these are easy, some of these are not. Derivative of x squared, super easy. Derivative of 1, super easy. It's a constant. This guy, I have to be careful. I have to be careful. Because y itself is, just very loosely speaking, think of y as a function. I just don't know what it is. Now, I know it's not actually a function. I just said it's not a function. Now I say it's a function. It's something that is affected by x. Now, just to have our words familiar, and because I can sort of cut it off, at least if I cut a piece of it off, there, that piece is a function. So it's okay, just for our understanding. See y as a function of x. I just don't know what it is. If I knew, I could find the derivative. I don't know what it is. What this is asking me is to find the derivative of a function of a function. It's the square function applied to the y function. This is the chain rule. This, in the square brackets, is a function of a function, y squared. Y itself, it's not the variable, it's a function of the variable. And then I square it. That's a function of a function. So the chain rule is going to come in two parts. First part says, take the derivative of the outside function, as if the inside function is the variable. Now, whether I call it u temporarily, whether I call it y, it's that something squared. Derivative of the outside function, 2y. Now, the derivative says, take the derivative, the chain rule says, take the derivative of this inside function, which is just y, which I don't know, so I write it down because I'm trying to find it. Okay, so this is where people get a little tricky, a little confused. But there's a simple rule to remind you when it's the chain rule. When the letters here are the same, then I don't have to worry about it. When this x, that's why I like the big D notation. When the x, which is the independent variable, is not the same as the variable that I see in my square brackets, it's the chain rule. Because that variable is a function of the independent variable. So if the letters don't match, watch out for a catch. If the letters are not the same, you have to use the chain. Huh? You like that? I like that. So it's very easy to know when the chain rule is in play and when it's not. The letters don't match, watch out for a catch. Letters aren't the same, you got to use the chain, whatever works for you. Let's summarize this. 2x plus 2y times dy dx. And some people are bothered by the fact that I have this dy dx. Of course I have it. I don't know what it is I'm trying to solve for dy dx. So I have negative 2x over 2y. I can simplify that, negative x over y. Now I have it. And I can now say things like, okay, at x equal to 0.5. Well, in this case, I'm going to have to be a little bit more specific. Which point are you looking at? Because there are 2 points corresponding to x equal to 0.5. Which one do you want? I want the positive one. What is happening? Okay, well, this derivative says, which often happens when I work with relations, it says you need the x coordinate and the y coordinate if you want to find the derivative. If you want to find the slope of the tangent line, you're going to have to give me both coordinates. Okay, well then I go back to my original equation, plug in the x value, find the y value. So I get 0.5 squared plus y squared equals 1. So y squared is going to be 1 minus 0.5 squared. I'm probably going to have to open my calculator here. And then y is simply the square root of that. Whoopsie. Y is simply the square root of that. So let's just calculate it. Of course, now it's installing updates. Y. Just trying a different calculators may be a mistake. Let's just go back to MathBot. MathBot always works. Well, not always. So I have square root of 1 minus 0.5 squared. And you should also get 0.8660 if I round to 4 decimal places. That's this y coordinate, right? Okay, great. Now the derivative takes both. And then I can calculate it. So the slope at this point is negative 0.5 for x, 0.8660 for y. Let us see what that is. Negative 0.5. Of course, remember when I do this, I always use the most accurate versions of the numbers. What do we get here? Negative 0.5774 rounded. Does that negative make sense? Negative a half roughly? Looking at the graph, yeah, negative slope, not too steep, a little flatter than 1. But of course, I don't know exactly how flat is a little flat. That's not really the point. The point is that there are things more general than functions that have a graph, that have nice graphs, for which I can ask the slope and tangent line question. Therefore, the derivative question, how do I do the derivative? How do I find the derivative, rather? Implicit differentiation. Implicit differentiation is the key. In that implicit differentiation, some parts are easy, some parts are maybe a little new. Let's do another example. I'm going to go to 11.1. In our problem book, I'm just going to randomly pick one of those. They don't have numbers. I will pick, which one do I like? 3x cubed minus 8y squared equals 10y. Now, if you think you can easily solve for y, then I'm sorry, I do not share your optimism. But that's okay. I don't need to. Let me just check. What's the actual question? For each of the following, find the derivative of y with respect to x. So they don't actually have a point that they're interested in or anything. Okay, that's fine. Just our first basic question to practice implicit differentiation. So it's a differentiation, derivative of the left, whatever the left is, times derivative, not times, equals derivative of the right-hand side, whatever that is. Now my goal, remember, is to find dy dx. Okay. Now I'll break this up by the difference property, just because I want to. 8y squared equals, handle all these derivatives in a second. Now I remember to watch out for the letters matching. The letters match, there is no catch. 9x squared. The letters aren't the same, you got to use the chain, because this inside the square bracket is a function of a function. Derivative of the outside function, 16y. Derivative of the inside function, dy dx. Done the chain rule now so many times, it just looks a little strange, perhaps. It isn't anything different. Oh, the letters don't match. Watch out for a catch. It's a function of a function. The inside function, I just don't know what it is. It's like the u. At that stage, I don't know what it is. Only if I look back at the end. Derivative of the outside function, 10. Derivative of the inside function, dy dx. Remember, this is what I'm trying to solve. I'm trying to find dy dx, so I'm solving for dy dx. So I need to group all the like terms together. Let's maybe move it to the other side and then flip everything around, because why not? Not equal. Plus 16y dy dx. And I have 9x squared left. Right, this guy moves to the other side, then that becomes my new left side. So I have 10 plus 16y times dy dx, taking it out as a common factor. I just like to write it at the end. Equals 9x squared. That does not look like a 9. Does not look like a 9, but I could easily misread that as a 7. And then lastly, dy dx is 9x squared over 10 plus 16y. And really, whenever my derivative, to a degree, depends on both x's and y's, yeah, the original one was not a simple function. And even if it was a simple function, honestly, even if it was a simple function, implicit differentiation is always going to work. I'm just going to have, oops, not that one, over here. Even if I have a super simple function, the implicit differentiation is still going to get me there. It's not new. It's just expanding my technique for finding a derivative. So no harm done with implicit differentiation. It's like the quadratic formula. If I have a quadratic function and I'm not sure if I can factor it, I think I can, but I can't see it. Who cares? The quadratic formula will tell me whether I can factor it or not. It's still the same. Not changing things, it's just expanding, allowing me to do more things. Right, so let's maybe expand on this if I go to the interwebs and look for a place where I can graph some stuff. Just check my screen, looks okay. Sort of. Can make that smaller once I have the function, okay. So I want to type in the function here. Now I don't remember what the function was. Let me just open this again. This is now the not function, sorry, the original equation, right? 3 times x cubed. Just ignore things that happen on the way. It doesn't know I'm done. It doesn't know when I'm done. 8y squared equal to 10y. Now go. And you see, let's see if I can zoom in here and make it features pretty. Let's get rid of that. Whoopsie, now I'm too zoomed in. There we go. That looks pretty good. See, that's some weird graph shape that I didn't know. That's okay. It's a nice smooth graph. I could ask a derivative question. Let's maybe do that and do one example properly. Even though they don't, I could take things like problem 11.2 and just do the same thing so I don't ruin 11.2 for you. Now we're not going to go in a test and ask concavity and things like that on these. We're just trying to lay a foundation for implicit differentiation, finding the derivative of more complicated equations so that we can use that in our practical questions. Okay, so don't worry about 11.2 that much. But I do have the time, so why not? Let's wrap it up by picking a point. Where do I like? What do I like here? Maybe a 1. That looks pretty good. At x equal to 1. I don't know what the y value is. I don't know. Off the graph, it looks to be 0.25, but I can't be sure, right? But there is a slope. Good there. I like it. What is that slope? Now I know it's not a function. There's another one here at the bottom as well, which looks to be negative 1.5. So let's just see. What do we do? But let's expand on this. I'm going to leave that page open and just make a new page. I want to make it as complicated as possible. Oh, let's do a couple. So you see the hard one and the easy one. Let's take this. Where am I now? Here. It's gone. Why is it gone? There we go. Let's pick one point that's easy. I think this one maybe. Negative 1 and negative 0.5. Whoopsie. Slope at negative 1, negative 0.5. Right? They could give me the point completely. What is the slope? Slope is simply the derivative with those values plugged in. So 9x squared, 9 negative 1 squared over 10 plus 16 times y. 16 times negative 0.5. Let's calculate it. That's just 9 divided by, let's do it anyway. I know we can do it in our heads. 10 minus 8, right? Half of 16. 4.5, 4.5. Does that make sense? Look reasonable? Where was it? Over here, right? It's pretty steep. Yeah, I believe that's a 4 slope. And positive. Looks pretty good. Yeah. But I can't confirm that, right? I can't say, oh yeah, 4. But I believe the 4.5 slope. It should definitely be positive. It's fairly steep in a 1 to 4 ratio. Yeah, roughly. Yeah. What if they ask, just so I can prepare you, slope at x equal to, what did we say? Maybe 1. Maybe 1. Now the problem is for that, I need both the x and the y coordinate to find the derivative at that point, which is the slope of the tangent line. I don't have the y value. I need the y value. The problem is I need the corresponding y value. That is the pickle, and that's almost more work than anything else. So if I go to my original equation and plug in the x value, I get x is just 1, right? So 3. Let's say here at x equal to 1, I have 3 minus, because it's 3 times 1, minus 8y squared, 8y squared equal to 10y. And I have to solve for y. Let's clean this up a little bit. 8y squared plus 10y minus 3 equals 0. Move everything to the right. And now I just have to solve for y. Quadratic formula. Do it. Negative b plus or minus square root of b squared minus 4ac, c is negative 3, over 2 times a. I like to calculate the square root first. I don't know, just habit. What is inside that square root? It's 100 plus 4 times 8 times 3. 196. Ooh, 196. Is that 14 squared? Square root of 196. That is 16. Oops, sorry. So that is negative 10 plus or minus 14 over 16. Oh, that's nice and convenient. I just randomly picked this one. Wow, it's nice. Good job, me. So y is gonna be negative 10 plus 14. That's 4 over 16. That's 0.25. Or y is going to be negative 10 minus 14. That's negative 24, right? Negative 24 over 16. Negative 1.5. No, yes, it is. Negative 1.5. And of course, it makes sense that I get two y values. It's this top one and this bottom one. It's not a function. For a single x value, I get multiple y values. So they would have had to specify, which one do you want here? Oh, you want both. Okay. So then at 0.1 and 0.25, I'll get a slope at 0.1 and negative 1.5, different slope, depending on the symmetry, right? The symmetry here is pretty strong, it looks like. So there might be a strong relationship, an obvious relationship between these slopes, but it won't be in general. 9 times x squared, 9 times 1 squared over 10 plus 16y, 10 plus 16y, and this one's the same, 9 times 1 squared over 10 plus 16, but a different y value. What do I get for the top one? I don't know. Calculator time. 9 divided by, what is that, 14? It's a quarter of 16 plus 10. And I get point, whoopsie, not that line, 0.6429 rounded. And then the next one, 9 divided by 24, it's negative 14, isn't it? Negative 14. Yes, we saw the symmetry already, so it kind of was expected. But visually, I can't say that it's exactly right. This could have gone a little bit different. It just looks the same. It's hard to say. We want to always rely on our calculation instead. But there we go. Done. So this was just a little bit of practice to lay the foundation for how to find derivatives in more complicated equations where I don't have functions, or I just don't know, or I couldn't be bothered to solve for the variable to find a function. So, oopsie, I see what happens here. Let's change the display here. So that was good, I hope. Our goal after this is to shift towards practical problems where different measurements are changing, like a balloon. The volume is changing with the radius of the balloon if it's a sphere. And how are those things related? There are things that are dynamically changing yet related to each other, and derivatives play a role. So we want to have some time to handle these kinds of questions because we want to see some practical application of derivatives now and then at least. All right. Are there any questions at this stage? All right, then until next time.